Okay, this lecture is a continuation of chapters 14 and 15, instrumentation. These are the enhancement tools. There will be a section of matching that involves enhancement tools, plus you should know the basic function of each of them. So let's start with coded excitation. So this is a sophisticated method of improving image detail. Okay, we want our detail resolution to improve. And it does this by creating long pulses with a wide range of frequencies. Now, I've bolded the following terms like long sound pulses. And let me underline them here too. With a wide range of frequencies, because some of the enhancement tools sound very similar. So it's really good if you can kind of point out some of the differences or some of the key things that go along with the tool itself. So coded excitation uses long sound pulses with a wide range of frequencies, and the overall goal is to improve our detail resolution without increasing the risk of peak intensities. And this is a function of the pulsar. For more information on coded excitation, and there's some more pictures and so forth in your book on page 253, he goes into a little bit more detail. So just to reiterate, the key things about coded excitation are it uses a wide bandwidth. Okay, so you have a range of frequencies and long pulses. Okay, that is how coded excitation actually works to improve detail resolution. Spatial compounding. On some systems, they refer to it as crossbeam, and other systems, they refer to it as SONOCT. So basically, these three names really do the same thing. Now, this is good and bad. Okay, so what's going on in this is data is compiled from different imaging angles, and then the frames are placed on the display overlapping, and it produces one single real-time image. Now, the purpose of it is to reduce speckle on the grayscale and to minimize shadowing, and it has its place. There's a time and place when we want to minimize shadowing. If we want to get through like ribs and they're causing us, again, a distraction for what we're trying to accomplish, like we're trying to get to a position in the liver where we see a mass and we can't really get to it real well, coming in from different angles around the bone might help minimize some of that shadowing and allow us to see that structure. However, you do not want to use spatial compounding, crossbeam, SONOCT, whatever your system calls it. You don't want to use that if you're trying to prove that there's a stone, let's say in the gallbladder, if this is the gallbladder, and there's a stone here, because proving that this is a stone means we have to show that there's shadowing coming from it. So sometimes we prove pathology because it has an associated shadow with it. That tells us a little bit about what we're imaging. So in the case of whether it be a kidney stone or a gallbladder stone or something like that, you do not want to use this enhancement tool. You only want to use this when you want to get around certain bones that are obstructing our view by coming in again from different angles. So if there was like, say, a bone here and coming in from different angles and sides, we can get different views, not just the head-on view, and that will minimize shadowing. So know what it does and know when you can't use this enhancement tool. Frequency compounding. Reflected signal frequencies are narrowed down and compounded. The image is then created by a limited number of frequencies. So with this enhancement tool, they use a narrow bandwidth that's compiled together, and the purpose is to reduce noise and speckle. And speckle is basically undesirable echoes on the display that you don't want there, and they degrade your image. So that's the way frequency compounding actually works. Edge enhancement is designed to make the picture look a little bit sharper by emphasizing the edges of whether it be a mass or the gallbladder or anywhere you'd have a little shadow along the edges. This is going to make that even a little bit more pronounced. So this method increases the image contrast in the area immediately around the edges. So they're pointing here to these little edge shadows here and making, again, them a little bit more pronounced. So this method increases the image contrast in the area immediately around the edge, creating highlights to make them appear more defined. Temporal compounding, often tested on the registry as persistence. And basically it does have a purpose, and it works really, really well for color, more so than grayscale. So I'm going to show you how this works. Okay. So with persistence, which they typically refer to it as, but it can be referred to as temporal compounding or temporal averaging, it takes previous frames and then superimposes the previous frames on the most common or most current frame. And the result of this compounding of frames gives us better image quality, and especially with color. So if you look at this first frame here, okay, this might be the result of one frame. Then you might have, let's say, a second frame, and it has a picture as well of the vessel. And let's say there's some color, but now the color is filling in more around these locations that weren't done on the first frame. So if you take this frame along with this frame and put them both on one final frame, you're going to get the filling in here that you had in this bottom image and the filling in through the center that you had in the first image. So basically what we're doing is taking multiple frames, and the little bits of color that were showing up in each individual frame will all show up in the final frame. So it works really neat getting good fill-in from edge to edge in vessels when we use persistence or temporal compounding with color. So it's most noticeable there. Fill-in interpolation is something that happens automatically. This isn't like a tool that you are going to adjust or use. The others, you have a button for that. What this does automatically is it takes gaps of missing data. When you send in, machine sends in rather, multiple scan lines, okay, there's always a little section that might be missed. So what it does is it takes a shade of gray that's similar to the two scan lines and fills in the gap with a shade of gray that fits between the two samples. So gaps or missing data exist between each scan line. And interpolation uses grayscale levels from neighboring pixels to fill in those gaps so that the picture appears smooth and a more consistent shade of gray. So basically, it's going to pick neighboring grades and fill in the missing data. So it's sort of guessing what it might look like. And then, of course, panoramic imaging. I think most of you have phones or cameras that have panoramic imaging. Some systems have this as well. It works really well with vessels. This is a picture here of an infant's spine, and we're able to expand. What we would normally have is probably this would take 3 different images, and using the panoramic imaging, it allows the transducer to move along the patient's anatomy and blend those image frames together to form one longer, wider field of view. So it's no different than panoramic views or pictures on your camera. So all of these controls you can adjust or choose to use, with the exception of the fill-in interpolation. Okay, that's going to be done automatically. Okay, so again, this section, know the definitions, know what makes them different. I tried to highlight those things when they start to blend together, and then be prepared to do a matching section on enhancement tools as well.